All right, number 4 says, in this problem, we wish to maximize the production of a certain good under a budget constraint. Suppose that production F is a function of two variables, x and y, which are quantities of two raw materials, and that the production level, if I use x units of raw material 1 and y units of raw material 2, is given by this expression, x to the 2/3 times y to the 1/3. If x and y are both purchased at a price of $1,000 per unit, what's the maximum production F that can be obtained with a budget of $3,780? Okay, one thing to point out here is that since x and y denote the number of units of these two raw materials, in particular they're non-negative values. Now for our budget constraint, since raw material 1 is $1,000 per unit and we're using x units of it, I'm going to spend a total of $1,000 times x on raw material 1. And likewise, I'm going to spend $1,000 times y on raw material 2. And the sum of these two quantities is the total amount I'm going to spend. And if I want to use up the full budget, I want the sum of these two quantities to equal the full $3,780. And notice that this equation can be rewritten as x plus y equals 3.78. All right, I'm going to go ahead and draw a picture of this budget constraint line. And one thing to highlight about this line is that if I choose any point on this line, say the point 1, 2.78, well, this is telling me if I use 1 unit of raw material 1 and 2.78 units of raw material 2, then since the coordinates of this point satisfy this constraint equation, I'm going to be using up the full budget. Okay, now if I were to choose a point below this line, say down here, where x plus y is less than 3.78, well then I wouldn't be using up the full budget. And if I were to choose a point above that line in the blue region, where x plus y is greater than 3.78, I'd be exceeding the budget, right? I couldn't afford that. So whatever combination of x and y I choose, right, to maximize production, okay, the corresponding point, xy, must lie on this green constraint line. Okay, so with that in mind, let's go ahead now and turn to the level curves of our production function f. Okay, so these level curves are going to correspond to all the combinations of x and y that will yield a certain fixed production level c. So I set f of xy equal to c, so that implies x to the 2/3 times y to the 1/3 is equal to c. Now if I divide both sides by x to the 2/3 and cube both sides, I get that y is equal to c cubed over x squared. And I'll go ahead and plot two of these level curves. So here is where c is equal to 1, and here's where c is equal to 3. Now as I just noted, right, we need to choose a point xy on the green budget line, right? And so if I'm thinking about a specific production level, like c is equal to 1, if I were to choose the point where this level curve intersects this budget line, say this point or this point, right, those points would be telling me, right, the amount of x to use and the amount of y to use to yield a production level of 1. Okay, now notice for all the points on the blue level curve where c is equal to 3, they all lie above the budget line. Right? So if I were to use any xy combination coming from a point on the blue level curve, I'd actually be exceeding the budget. So in fact, it's not possible for us to have a production level of c equals 3. Okay, now let me jump over real quick to Desmos to illustrate this further. So I have our budget constraint line in green here, and here's our level curve when c is equal to 1. So for example, when I look at the intersection point here, if I use 0.557 units of raw material 1 and 3.223 units of raw material 2, okay, I'm going to get a production level of 1. Okay, now, what do I ultimately want to do? I want to maximize production. Okay, so in other words, I want to find the largest value of c, right, because c here is our production level, such that the level curve, f of xy is equal to c, still intersects this budget line. As I already noted, right, c equals 3. Yep, that's not possible for us, right? Because all points on that level curve exceed our budget, right? Because they lie above the line. So I'm looking for the largest value of C so that this level curve still intersects our budget line. So notice if I increase C from 1, okay, I'm still intersecting. I want to keep going until I just kiss this budget line. And it looks like, see, if C is 2, it looks like that's about right. It looks like this level curve is tangent to my budget line at the point of intersection. Okay, so at least approximately 2 will be my at least guesstimate here. Okay, so C is what looks to be about 2 from Desmos is going to correspond to our optimal point here, right? So this combination, so whatever the coordinates of this point P are, right, they're going to give rise to the largest production level, which appears to be about 2. And we note here that the level curve of F is tangent to our constraint line. Okay, cool. So now, I gotta leave a little space here. Okay, so let's go ahead and solve this using what we call the method of Lagrange multipliers. Okay, so we have this function to maximize, that's our production function. We're going to refer to this as our objective function in the next couple videos. And our constraint, I'm going to write this as g of xy equals 3.78, where g of xy is just x plus y, right? That's really just a restatement of our budget constraint up here. Okay, so now what did we just say? We said that, right, at this point where the level curve here is tangent to our budget line, right, that point P is our optimal point, right? The coordinates of that point are going to give rise to a maximum production level. And I note here that since the level curves of F and G are tangent at P, right, that's what I'm saying up here, if I look at the gradient of F at P, which I know is what? It's normal to this purple level curve, and you see that here in red. It's got to then be parallel to the gradient of the function g at P, right? And I know that the gradient is normal to the level curves of g. And notice, right, the way I've written the constraint line, right, g of xy equals 3.78. That's just a restatement of this equation. X plus y is 3.78. It's a level curve of the function g, right? So the gradient is perpendicular, or in other words, normal, right, to that green line. And so yellow and red, these vectors have to be parallel. And so, right, that means that there's some scalar, I'm going to call that scalar lambda, this is known as a Lagrange multiplier, such that the gradient of f is equal to lambda times the gradient of g. Okay, so now, since I have both of these functions, let's go ahead and actually take this further and solve specifically for our max production. So here's the gradient of f. Okay, so I take the x derivative of f as the I component and the y derivative of f for the j component. Here's the gradient of g. Since g is just x plus y, the x derivative is 1 and the y derivative is 1. So then I set the gradient of f equal to lambda times the gradient of g, where again lambda is just some scalar. Okay, so now just on the left side replace the gradient of f with this expression I have up here, and on the right lambda times the gradient of g. Well, since the gradient of g is just 1, 1, if I multiply that vector by lambda, I get the vector lambda comma lambda. Okay, so now I just equate I and j components. The I component is here, that must equal lambda, and the j component is here, that must also equal lambda. Okay, and now notice here that since both of these quantities are equal to lambda, I can go ahead and equate those quantities. So I have 2/3 x to the negative 1/3 times y to the 1/3 is equal to 1/3 times x to the 2/3 times y to the negative 2/3. Okay, now if I go ahead and rewrite that, I get that simply 2y is equal to x. All right, now I'm getting there. I need to make a little bit of space here, but how do I go about finding, now that I know that 2y is equal to x, the coordinates of this point P? Well, right, I know I'm looking for, in particular, a point on the budget line. So what I'm going to do is use this condition and plug that into our constraint curve, right? If x plus y is 3.78 and x is 2y, just replace x with 2y. 2y plus y is 3y. If 3y is 3.78, we get that y is 1.26. And since x is 2y, if you double y, you get x is 2.52. Okay, awesome. So now let's go ahead and, here, I'll leave that up actually. Let's go ahead, I need to make a little bit more space here. For our conclusion, okay, I want to use 2.52 units of raw material 1 and 1.26 units of raw material 2. If I plug those into my production function, right, I get 2.52 to the 2/3 times 1.26 to the 1/3. If you use your calculator, that is 2.000125, right? So when we were eyeballing it on Desmos, I was saying, gee, at c equals 2, it looks like we're pretty darn close. So if I put in the actual value we just computed, what was it? 125, at least approximately. Okay, with that choice of c, and if I zoom in, aha, that actually now is tangential. Okay, awesome. So this will be our maximum production possible given this budget constraint. Okay, so now in this example, we just illustrated this method of Lagrange multipliers. In the next video, we're going to go ahead and describe the method in more generality, and then we'll just look at some additional examples. All right, see you there.